Hi everyone. Today we're going to be talking about a couple new aspects of integrals. So one, we're going to be talking about some properties of integrals. And actually some of these will be familiar because we've talked about them, just haven't formally stated them as properties. And then we're going to find out how we find the total area under the curve. So first, the properties. This first one, order of integration, we've actually talked about before. And all this says, I'm going to write the integral from b to a of f of x dx is equal to the opposite of the integral from a to b of f of x dx. So in other words, if we switch the order of integration, we change our upper and lower limits of integration, then we're going to change the sign of that integral. And so we talked about this a lot when we were looking at graphs, and we talked about kind of going backwards. The second property is our zero property, and this says if I integrate from a to a of f of x dx, that's going to be 0. Because obviously if my lower limit of integration is the same as my upper limit of integration, we haven't accumulated any area, so the value of that integral is 0. Okay, the next one is our constant multiple. So we're saying if k is a constant, so if k is a constant, then the integral from a to b of k times f of x dx, we can just pull that constant out. So that's the same as saying the constant times the integral from a to b of f of x dx. So we can just pull that constant out and integrate the function. Okay, sum and difference of integrals. So if I have integral from a to b of the sum or difference of two functions, that's just equal to the sum or difference of those integrals. Okay, next one is called the additivity function. And here's what it says. It says the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. So graphically it looks like this. If I have some function, let's say here's a and b and c. All it's saying is that if we take the area from a to b of f of x dx, so I know I'm accumulating this area under the curve, and then I add the integral from b to c, we know that's just adding in this area. What that's going to give us is the total area under that curve from a to c. Okay, the next one is domination here, and here's the setup. So it says if f of x is greater than or equal to g of x on the interval from a to b. So graphically what we're looking at is something like this. If I have some function f of x and another function g of x, so if f of x is greater than or equal to g of x for all values of x in this interval, sorry, this should be a closed interval here, then we know that the integral from a to b of f of x is also going to be greater than or equal to the integral from a to b of g of x. And again, that's because we're talking about the area under the curve. So if I'm talking about the area or the integral from a to b of f of x dx, I'm talking about this total area. But if I'm talking about the integral from a to b of g of x dx, I only have the area here under this curve. So if f of x is greater than g of x, then that integral is going to be greater as well. Let me specify that this is from a to b. All right, so our last property is called the max-min inequality. And here's what this says. the maximum inequality looks like this. And so I'll write it and then we'll kind of look at what this means. So if I take the minimum value of f times the interval of b minus a, that's going to be less than or equal to the integral from a to b of f of x dx, which is going to be less than or equal to the maximum value of f times b minus a. So essentially what this is doing is giving us a lower bound and an upper bound for the value of that integral. So again, let's go ahead and take a look at what this might look like. So I'm going to just make up a graph here, make up a curve. I'm going to make it look like this. Okay, and I have from A to B. So I know here that the integral from A to B of f of x dx is just going to be the area under that curve, or between the curve and the x-axis. So that's the value of the integral, is all this area between the curve and the x-axis. So now we said the lower bound is the minimum value of f times the interval b minus a. So graphically, let's look at that same curve roughly. And we are from A to B. Now, here's the minimum value of f here. And I'm going to multiply it so we can think about that minimum value of f as being the height of a rectangle. So here's my height. And then I'm going to multiply it by the base of that rectangle, b minus a. So if I create that rectangle, this is the area that I'm capturing. That's represented by the minimum value of f, so I'll put that here, minimum of f times b minus a. So we can see that this is going to be less than this value. Now for our upper bound, again, roughly the same curve here from A to B. Now our upper bound, now we're taking the maximum value of f and multiplying it by that same interval from A to B. So now you can see we're capturing a whole lot more area here, and that's what gives us our upper bound. And in the examples we'll do shortly here, I'll show you an application of when we would use this theorem. All right, so let's go ahead and do some work with these properties. All right, so it says use the rules for definite integrals and the following known integral values to answer the questions. So we're going to use our properties here. So my first integral, so it says evaluate them if possible. And again, we're going to use our properties and these three known values. So if I want to find the integral from 1 to 4 of f of x dx, I notice pretty quickly that it's a lot like this one, except that order has been changed. So we're going to use our order of integration property. I'm just going to make a note there in case you're looking back. So that's order of integration. And what that tells us is that this is just going to be the opposite of the integral from 1 to 4 of f of x dx. I know that value is a negative 2. So I have opposite of negative 2, and that gives me a value of 2 for that integral. Okay. Now, my next one, my integral is from negative 1 to 4. So what I notice here is that I have an integral from negative 1 to 1, and I also have the integral from 1 to 4. So this is going to be additivity here. So I know that this is equal to the integral from negative 1 to 1 of f of x dx plus the integral of 1 to 4 of f of x dx. And then I can just add those values. So 5 plus a negative 2 is going to give me a positive 3. All right, now for the next one, I actually notice I have a couple things going on. I notice I have my plus sign here. So that's going to give me a sum. I'm going to use that sum rule. But I also notice here I have these constants. So that's going to be my constant multiple rule. So I'm just going to make a note here. We're using our sum or difference rule plus our constant multiple rule. So if I were to show all the steps here, and ultimately you won't need to do this, I'm just showing it to illustrate it now. So really what we have here, I'm going to use my sum or difference rule first to split this up. So I'm going to have the integral from -1 to 1 of 2 times f of x dx plus the integral from -1 to 1 of 3 times h of x dx. So that was using my sum or difference rule. Now I'm going to use constant multiple rule to pull out those constants. So that's going to be equal to 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. And so now I can take the values that I know from the top. So it's going to be 2 times the integral from -1 to 1 of f of x dx is 5, plus 3 times the integral from -1 to 1 of h of x dx is 7. So I get 10 plus 21, which gives us a value of 31. Okay, now for number 4, the integral from 0 to 1 of f of x dx. I don't have anything that tells me the value of the integral from 0 to 1. And a lot of times it's tempting to take this one and say we'll just split it in half. The problem is I don't know anything about this function. I don't know that it's symmetric about the y-axis, so we have to be careful here. This one is actually not possible. We can't evaluate it using the properties that we have. Okay, for similar reasons, for number 5, again, I know it's from -1 to 1 is 7, but we can't assume that we can just double that area. So again, we don't have any property that we can apply here, so this one is not possible. All right, and one more using our properties then. So let's see, here we have our sum or difference property. So I know that this is equal to the integral from -1, let's scooch this up, -1 to 4 of f of x dx plus the integral from -1 to 4 of h of x dx. So now if I look back up, I know the integral, actually, I know I can get -1 to 4 f of x dx by doing the additivity property. The problem is here, I only know the value from -1 to 1 of h of x dx, and I don't have information from 1 to 4, so again, this one is going to be not possible. All right, number 1, we kind of jump back here. I'm using the max-min inequality. I actually want to go through that one in class together just to make sure we all understand what's happening with that one because it's a little more complex. So we'll leave that one for now, and we're going to spend the rest of the time talking about how we find the total area between a curve and the x-axis. So we're going to jump over here to page 47. Again, talking about the difference between integrating versus finding an area. So remember, when we integrate, all the areas that are above the x-axis are counted as positive. So here, if I'm integrating here, I'm going to have a positive area under this portion of the curve and under this portion of the curve. And then all the areas that are below the x-axis are counted as negative. So when we integrate, essentially what we're doing is adding up the purple and subtracting all of the orange. So the question is now, how do we find the total area between a curve and the x-axis? So when we want to find the area between a curve and the x-axis, And here I want to point out, when they specify that we're finding the area of the region between the curve and the x-axis, that is what we mean by the total area. So we'll use that verbiage to indicate the total area. Okay, so now when we do that, we want to find the sum of all the areas. So in other words, we don't make the areas below the x-axis negative. So we're going to spend the rest of the time figuring out how we make that happen. All right, so now, again, finding the area between a curve and the x-axis, this means we want the total area. If we're asked to find that area, we're being asked to find the total. So somehow I have to figure out which area is going to be positive and which are negative, and then just add their absolute values. So here's how we're going to do that. First, we're going to find the zeros of the function. We're going to divide that graph up into sections using the zeros. We're going to integrate over each section separately. And then we're going to add the absolute values of those areas. So let's take a look at a problem. So we want to find the area of the region between the curve y equals 4 minus x squared over the interval from 0 to 3 and the x-axis. So here's what we're going to do. The first thing we're going to do is find the zeros. So we're going to take that function, 4 minus x squared, and we're going to set it equal to 0. So we know x squared is equal to 4, and so x is positive or negative 2. So now, if I'm finding the area over the interval from 0 to 3, I know I actually have to integrate over two separate intervals. I'm going to integrate from 0 to 2, because that's one of my zeros, and then I'll integrate from 2 to 3. So we're going to integrate our function, 4 minus x squared dx, use our antiderivatives for x minus x cubed over 3, and we're going to evaluate that from 0 to 2. So if I plug in 2, I'm going to get 8 minus 8 thirds. I'm subtracting my lower bound. That's just going to give me 0. So if I convert this to a common denominator, I'm going to get 24 thirds. So 24 minus 8 is going to be 16 thirds. So that portion of the area I know is above the x-axis because that integral is positive. Now I'm going to do the same thing from 2 to 3. So I have 4 minus x squared dx. My antiderivative is going to be the same. And I'm integrating from 2 to 3. So I'm going to evaluate my upper limit there. So I have 12 minus 27 over 3 is going to be 9. And then minus, well, when I evaluate it at 2, I know that was 16 thirds. So I'm going to have 3 minus 16 thirds. Again, I'm going to make it a common denominator. So I have 9 thirds minus 16 thirds. So I get a negative 7 thirds. So again, since we know this value is positive, this was above x. And this value was negative because that area is below the x-axis. But again, for total area, I just want to find the total area. I don't want to take into account that sign. So now I'm going to go back up here. My total area, I'm just going to add the absolute value. So I have 16 thirds plus the absolute value of negative 7 thirds, and I get an area of 23 over 3. So that's how we have to do this by hand. Now, we have a much easier way of doing this if we can use the calculator. So in number 2, we're asked to find the area of the region. Remember, if it's asking for the area of the region between the curve and the x-axis, again, that's the total area. So now it says using nint. So that's our calculator function. So here, since we only want to consider those areas positive, when we're doing this on the calculator, all we need to do is we're going to integrate from negative 3 to 3. That comes from our interval here. My function is x times cosine of 2x, but now since I only care about, or I want to make all of the area positive essentially, we're just going to integrate the absolute value. And then we're going to use our calculator to do that. So again, if I go to my calculator, I'm going to do math. Let's get to here. Math 9 is going to give me my fn int. I'm going from -3 to 3. I'm going to use my absolute value function, and I'm going to integrate x times the cosine of x dx. Whoops, what did I do? Let's try that again. -3 to 3 times the absolute value of x times the cosine of x, there we go, dx. It's going to take a little bit to think here. And we get a value of approximately 5.416. Oh goodness, I put in the wrong function. Third time's a charm. Let's do this. -3 to 3. Absolute value of x times the cosine of, it should be 2x here. I missed that. All right, let's see what we get this time with the correct function. All right, and so our answer is 5.425. So just to wrap up quickly, I'm just going to add to our notes up here that if we can use our calculator, so on the calculator, we're just going to integrate the absolute value of f of x. All right, so that's it for today. Again, we'll go over that example on the max-min inequality tomorrow in class.